Hey, hello students. Today's class we'll continue where we left off in the previous session. So we solved about three numericals in the previous class. Um, so uh, as requested in the previous class, we'll solve one numerical which is having all negative values of these stresses, right? So this problem is a typical one where you have negative values. So if you see the convention here, so whenever these shear stress components are arrowed in this fashion, that means towards the top right corner and bottom left corner. So in these two cases, you assume it to be as a positive case. Whereas if it is in the other two corners, then you assume it to be as a negative case. And also you can see the stresses. That is the biaxial case. So in this case, you ignore this arrow. This is not an arrow at all. So actually, it is over here. Okay, so stress acting in this fashion. This is regarded as negative again. So it's trying to compress the body, right? So compression is usually taken as a negative. Okay. So the direction sense also you can keep it as sigma x. This is sigma x, and this will be sigma y, and this is tau xy. Biaxial value with shear stress. So that's how we encounter this. So also in addition to these two, you can see the question: state the stresses, state of stress in two-dimensional stress body. Should be determine principal stresses, maximum shear stress. So these two are typical. Sometimes you may have a third value also, like find normal stresses, normal stresses. So this means you need to find sigma theta and tau theta. Okay, so these are also given. In principal stresses, this just means that we are finding the principal sigma 1 and sigma 2, and this is tau max, right? So, but here, one more thing could be added here in the questions to extend it further. So that may be normal stress. So this we have to just plug in the equation available already with us into the solution and extract the values. Not much difficult as such. Okay, so let's solve these this problem here. So our objective to find the principal stresses and also the normal stress. So for which values, the equations are readily available in the handbook, right? Also here you can see the angle is not given. Okay, the plane at which you need to find is not given, but instead we have the stresses. So since the angle is not given, we cannot find this the value here of principal stresses. So that being said, some or the other angle should have been. So in case of normal stresses, right? So some angle should have been given. So let's assume some angle here. Since we have extended this question, let's extend the diagram also. Let's say you need to know theta at some angle that is equal to 30 degrees. So let this be given data because I've asked the normal stress also, right? So if normal stresses are required to be found, then you need also to find this theta. Okay, let's solve this problem. Okay, so here we are. Okay, let's try to solve this. So given data, so data is you have sigma x, which is 120 newtons per mm squared, sigma y is 80. Oh, I forgot the negative. We need to include that negative here. It is minus. Okay, minus values, negative values, because we are dealing with compression, right? This is compression, so therefore we need to include that minus. Okay, make sure you don't forget that. It's minus 80 Newton per mm squared, and also shear stress tau xy is, it's in the negative value. Negative. This is a negative quadrant, you can call it. So this quadrant and this quadrant here, you can call it as negative. So it is also minus 60 Newton per mm squared. So all values here, the stress values, they fall in the negative category. Okay. So that's all the data we need. Let's start off with the solution. So we'll go with the first one, that is principal stress. So note if he has asked the direction. Oh yeah, directions also asked. So if you want, you can write what all things you need to find also. So let's say to find, we need to find sigma 1 and 2, that is the principal stresses. Theta 1 and 2, that are, these are the directions. Then tau max and the direction of shear, the angle of shear stress, again theta 1 and 2. So note these are separate. This is for principal stress and this is for the shear stress. Also you need to find the normal stress, sigma theta and tau theta. This is somewhat like a worst case scenario, problem. Okay. So principal stress, we already defined this equation. So let's write it over here. The sigma 1 comma 2 is equal to sigma x plus sigma y by 2 and plus or minus under the root sigma x minus sigma y by 2 the whole square plus tau xy square. So this is given in data handbook, equation 2.34 and 35. Two equations just below the other, one below the other. You can directly go for the substitution. Sigma 1 comma 2 is minus x minus 120 minus 120 minus, again y is 80 by 2 plus or minus, you have under the root minus 120 plus 80 by 2 the whole square plus
Hello?
Yeah, tell me.
So sigma y is also in negative decimal, right?
Yeah, it is negative, correct. It is negative, you are right.
It's a okay plus. So plus in.
So it's plus here, that means we already have sigma y negative here, right? Minus 80. So I put minus 80. So plus into minus is minus, but here you have minus already. So minus 80 into minus is plus. So that's where the sign change has come in. I hope you got it. Right, so we'll calculate this. Just try to calculate this and obtain individually. Individually, you can obtain sigma 1 and sigma 2. Let me calculate. Side by side here we have -100. So this will come to -100 plus or minus under the root minus 120 plus 80 divided by 2 squared. You have 400 plus 60 squared. 4000 root of 4000 63.24. So you have square root of 63.25. Approximately this value. So now this is the point where it splits. Okay, your sigma 1 and sigma 2. So sigma 1 and sigma 2 you can calculate individually from this point. Oh, I'm sorry. You get root of 400. So the root won't be there. So this is just 63.25. Once you calculate all of this, now you will get 63.25. Right. So sigma 1 minus 100 plus 63.25. Yeah, sigma 1 is minus 36.75 and sigma 2 is minus, both are negative, right? So it's it will come to around minus 163.25. Okay, so this is in Newton per mm square. This is also Newton per mm square. Right. So these are your principal stresses, principal stress values here. You can see both are compressive type. Both are compressive type. So these will probably fail in a compressive fashion as predicted. Okay, sigma 1 and sigma 2, which is principal stresses, what we have found. So next is inclination. Inclination of this. Let's call this inclination. Inclination, that's nothing but the angles at which is at theta 1 and 2. So this is given in equation as half tan inverse of 2 tau xy over sigma x minus sigma y, and this comes in equation 2.36. So this is inclination of that principal axis, again which are split by a 90-degree angle here. Okay, let's try to find this out. So this is equal to half inverse tangent function of 2 into minus 60, which is shear stress, over minus 120 and 80, right? Yeah, 120 and 80 minus 120, again minus into minus plus 80. Yeah, that's it. So once you find out with this, you can find theta 1. You get theta 1, and theta 2 will be perpendicular to it. Theta 2, the other stress will act perpendicular to that. That means it is theta 1 plus 90 degree. Okay, so try to find that. Have everything here. Next part, we'll move on to the maximum shear stresses. Maximum shear stress. So maximum shear stress is given in an equation. Tau max is equal to plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. This is in equation 2.37. So if you see what that is, you can directly relate to this part here. See, this portion here is exactly like that. Okay, so the second part of the principal stress equation is nothing but your shear stress. So what we can do, we can extract the same values over here. Okay, so this we can relate directly to the one which we have just defined here. Okay, that's nothing but the second part of the principal stress equation. You can see everything is same. Only thing is the plus or minus is there in the before that. So what we can do, we can just write this part of the value here. 3.25, we can write it here as it is. So tau max is 63.25 Newton per mm square. That is again plus or minus. Okay, so that's simple as that. So that's our second answer. What is the maximum shear stress? Let's find this out. If you have calculated, you can post it in the group chat. So theta is 2 into 60 over 40. So tan inverse of that, put it in radians. 2 into minus 60 over how much? Minus 40. Tan inverse of that and half of that. So I'm getting an angle of 35.78. This is 35.78 degrees, and add a 90-degree to that. You'll get your second principal axis. So it's 125.78 degrees. Right. So that's it. The next, move on to angle of shear stress. Angle of shear stress. So angle of shear stress, again given in the data handbook, theta 1, 2 is equal to, I'll just verify this once in the data handbook. This is 25.38. Let me just check that. Yeah, it's here 25.38. This is the equation, right? So we'll use this. So no change there. Only the numerator denominator is different. So this is given as half tan inverse of sigma x minus sigma y by 2 tau x y. Same thing. Arc tangent means it's tan inverse. Okay. This is in 238. Okay. So this is equal to, let's calculate this, half tan inverse of minus 120 minus into minus plus 80 over 2 into minus 60. So if you substitute this, you'll get theta 1, and theta 2 is again theta 1 plus the 90 degree. Just add 90 to that, you will get your the second principal stress. We'll go back to the question. So this is the question given. We need to find one last thing, and as I told you, it's just an extension. You can find the normal stresses also. Sometimes we may ask you to find the normal stresses, which we have derived in the values there. Okay. So fine. So this is not a problem. Over 2 into minus 60. Tan inverse of that over 2. Right. You're right. So you get theta 1 as 9.22 degrees. I just add 90 to that to get 99.22 degrees, and that's it. So that's it with the angles of shear stress. Okay. Then one last thing remains as we are going back to the question. This is we are finding the normal stresses, sigma theta and tau theta. So for sigma theta and tau theta, you can go back to handbook, and the data handbook you can see here normal stresses on a plane at any angle, shear stress on a plane at any angle. Suppose you want to find in the question, okay, what is the stress at this particular angle, what is this particular angle. So at each and every point, if suppose if you want to find, you can just give an angle of theta and plug it into these two equations here, so you get your respective values. Okay. Let's do that. So third part of this question is you need to find normal stresses at theta equals 30 degrees. Okay, at that plane you want to find normal and the shear stresses. Okay, so that is sigma theta, which is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sine 2 theta. So this is given in equation. Let me check the equation. 232. This is 232. So directly you can plug and play. Just plug and play here. X is minus 160, 160, 120. 120. 120 minus 80 over 2 plus minus 120 minus minus of minuses plus 80 over 2 into cos 2 into 30 plus I don't think it's plus anymore, to be minus 60 sine 2 into 30. So solving this, I think you'll directly get the value of sigma theta. So similarly, we'll also put the equation for tau theta, that is the shear stress. So shear stress also directly given below the above equation, that is the 2.33. So tau theta. Just refer it for a second. Okay, right. So is sigma x minus sigma y 2 into sine 2 theta plus tau xy cos 2 theta as given in equation 233. Okay, so let's substitute the values. Then is there if there is any relation we can find out. Okay, there is no relation between the normal and shear stresses. Let's see. I need to substitute for this also then. So it's sigma x minus 120 minus of minus plus 80 over 2 sine 2 into 30 plus it's no longer plus because we already have a value of minus 60 cos 2 into 30. So again, direct substitution. You can try to find out the value in the calculator. 161.96. I think this works out. 161.96 newtons per mm squared. So this is normal stress value. And one last thing for shear stress. Try to find out one last for shear stress. Tau theta. I'm free anyways. So let me do it. 120 plus 80 divide by 2. Answer into sine of 2 3 the 60. Answer minus 60 into say cos 60. So I'm getting a negative answer. Let's check the value. I'm not sure here. I'm getting minus 47.32 Newton per mm square. Let's check this value. I've got this value here after calculating, and that's that. The tau theta, that's the value. Now we can put it. Right, so we have found everything required in the question. We have sigma 1, sigma 2. Yeah, we have almost arrived same answer. So we found sigma 1, sigma 2, theta 1, theta 2 with respect to the principal planes, and also tau max for the shear and normal stresses sigma theta and tau theta. Right, so that's how it's done. This problem would be asked for somewhere between 8 to maybe 9 marks or even 10 marks sometimes. Was a little bit, it's a little bit lengthy, I guess. It's about 8 marks, I can say. 2, 4, 6, 8, about 8 marks we can say about this problem, right? So that's it about the biaxial state of stresses and along with shear. So we'll move on to the next part. Okay, so this first unit is split into three parts. So this first part is about uniaxial, biaxial, triaxial stresses and shear components in two-dimensional scale. The next one we'll start with the static loading conditions. Right. Start a new sheet. Save this. Okay, save it. Save it. The next part, what we'll deal with is static stress conditions. Okay, so coming to the static stress conditions, so we know already what all loads we can apply. So So we have axially loaded type, right? So we have axial load. Suppose you have loads which are being applied in two directions. Let's say the first thing is for static load. The second unit, I think Basara sir is doing the fatigue or the dynamic loads. So the first unit deals with only static load. So what is static load? If you ask me, static load is nothing but it's a stationary force, which is acting on a member without change in magnitude or direction at any point of application. And this is with respect to time. Okay, so if you assume a component where just a uniaxial case, or even let's assume a cylindrical component for now of a cylindrical cross section. If you apply forces on any two directions here, so let's say I apply a tensile force over here and another tensile force over here. So this is just called an axial force condition. Okay. Similarly, if the forces, if they were opposite to this direction, you call it as a compressive force, right? So these are the two types of forces. So how would you write the equations for this? So let's say you wanted to find the deformation, for example. The deformation you wanted to find for this particular case. The deformation I'll just denote it by delta. So deformation denoted by delta. So what is the value of delta? Delta is nothing but it's change in length, right? So this deformation is nothing but the change in length. So this can be written as strain times original length. So you know the equation, right? Strain. What is strain? Strain is change in length to the original length L. Okay, this we already know. So there's this equation. I've just swapped it for this matter. Also here we know the Young's modulus. We can relate this. Young's modulus is written as stress over strain. Okay, Young's modulus is written as stress over strain. And what is stress written as? Stress you can write as force by area. Oh, I'm writing P here. Let me write force F. That is force by cross-sectional area. You link these two equations here. You can write stress as, or this value of strain as sigma by Young's modulus. So I'll just replace this as sigma by Young's modulus into L. So I'm just replacing this thing here with this. Okay, again, if I replace this stress with this equation here, so I'll get deformation as F L by A and E, where F is your force which you are applying on the component, L is your original length, A is the cross-sectional area, and E is the Young's modulus of this particular material. So that's how we calculate the said deformation. Okay, for any material, the deformation is like dependent on all these parameters here. What force you're applying, what is the length of the member, and what is the area, cross-sectional area here. So let's say this is the cross-sectional area of this body, cross-sectional area, and Young's modulus of the material. What kind of, is it the steel, is it aluminum, or those kind of things. So this is what we call as a first type of loading condition called axial load. So this is axial load. So similarly, we have several other axial conditions. So axial load also includes compressive cases. So same load if you apply in the opposite direction as I have told you here. So that case it is compressive. Okay, so let's move on to the next one. So I have a body here. Let's say, assume. So I have a body like this, and it is a, again, I'll say it is circular, like a cantilever beam kind of a thing. Am I going in angular direction? I don't know. So just bear with me. You're applying a load in this fashion. So what kind of suppose this is a force F I'm applying over here. So you can imagine what kind, how the deformation will occur, right? So you know that it will deform in this fashion. Right? Okay, the entire thing might go like this. Okay, for example, okay, the dotted fashion which I've showed, so it might bend entirely in this way. Okay, so what kind of this thing? So what word did I use? I used a word called bend, right? So that's the load. There's the second word I'm using here, that is bending load. Bending load. So bending load is just you are applying a force and it is being bent. Okay, so while bending, two parameters, two things occur. So what are those two things? Is you have two areas here. So you have, let's call this section A and section B. Section, or let's call this a point. Point A and point B. The 2 points over here. So A here is subjected to what kind of force? If you just you can imagine, right? What kind of force A encounters. So A, I'll say, so it is being pulled here. It is being pulled away from its fixture here. It is rigidly fixed, but because of the load applied, it is being pulled. So I'll say it is tensile behavior. And whereas at point B, if you see what is happening, it is being pressed inside. It's being pressed inside of this wall. So therefore, this kind of load is compressive. So both tensile and compressive are acting simultaneously. Usually in the previous case that never happened. So in this case you either had tensile or you had compressive, but here both are happening for one single direction of force application. Right. So this condition is called bending. Okay, when you have both kinds of stresses, tensile stress and compressive stress acting, so that time you call it as a bending force. Now in this case, you no longer call it a force, you call it as a moment. Okay, bending moment. Okay, so you have the force being applied in this direction here. Okay, and it is applied at a distance, at a certain distance. So this is the distance here between the wall and the force. There is some distance. I'll call this distance as L. So at length L, you're applying the force F. So now I can define what is the magnitude. So magnitude is again different, right? So I'll call this bending moment. Bending moment. So bending moment is denoted by MB, and it is equal to the force F times the length here. What is the length it's being applied? F into L. So it is given in Newton mm. Okay, that's the units. Okay, Newton mm. This is the bending moment. Then how is this categorized? So how can I link this with stress? So ultimately, I want stress, right? So when you go to any manufacturer for buying the material, so will ask you what will be the maximum stress, or what's the maximum stress you are putting on that material. So that's one of the parameters. So how do you convert this to stress? Okay, so here we come up with the governing equation, the bending equation or the governing equation, which we call. So that governing equation, you can find it again in the data handbook. Let me just show it to you. That is here, bending. All right. So this is the one. So I could have shown you this figure. You can see whenever there is bending moments being applied in both the directions here. So in that case, you can see the inner fiber, which we call here, is in compression. The outer one is in tensile. The dotted one is the original shape. So once you apply the bending moment, you have a compression and tension taking place. So we can link bending moment with stress in this fashion, where I is called as the moment of inertia and C is distance from the between the neutral fiber to the any one of the fiber. There's half distance you can call. Okay, so we can extract this equation here. Let me just take that. This is called general formula of bending. So we can link it using this equation. So this is general form of bending where I want to link my bending moment to stress. So what else are needed? You just see. So also needed here, I need what is I. Suppose I assume this rectangular cross section, then it will be just B, D, breadth and depth cube over 12. So these values also I'll tell you how to extract from the data handbook. For now, let's assume this rectangular bar. Okay, let's say rectangular bar, and it is being applied the eccentric, not eccentric, it's the bending kind of load. Similarly, suppose it was circular. Suppose it was circular, I would say my I would be pi times d power 4 over 64. So this also you can extract it from the data handbook. I'll show you how. Okay. And one more thing. So three things are done here. So MB we know. So we know MB. We need to find sigma B. That means we need I and we need C. Suppose I want stress sigma B. So I need to have at least the RX or the LX, some value. So let's just see how do you find. So C is nothing but half value of that. Suppose here C is just the radius, that is d by 2. Okay, here also it is the depth. Depth means this dimension here. So this depth divided by 2. Okay, so that's same case in both the things. So that's how you would calculate the stress value. So now, since I know these three values, I know bending moment, I know the moment of inertia, I know the length of from the neutral, the centroidal axis. Okay, centroidal axis is a central axis which I showed you in the this central axis, which you can see, the neutral axis. So from there to any of the inner or outer fiber is called the C, value of C, center distance. So that's how you get the value of C. So let me write it in a shorter form. So let's say it is MB by I equal to sigma by C. This is sigma B equal. This is bending stress. So this is not the normal, the usual value of stress which we used, right? So sigma B is written as MB C by I. So sometimes what happens is you can send this C to the denominator. So if you send to C to the denominator, you'll get like MB by I by C. Okay, so I by C, this value of moment of inertia by the neutral layer, the distance from the central fiber. Okay, what you call it as? You call it as a section modulus. That is denoted by Z. Z is also called section modulus. Section modulus, which is denoted by I by C. Okay, this is a small side note here. Okay, so therefore, you can write sigma B as just the bending moment MB by the section modulus Z. Okay. That's how you need to extract the values over here, right? So we'll continue. One last type of stress. So we have continued the axial. We have started with axial. This is the second type. That is bending. So we'll move to the last type of stress which we'll be encountering here. It is called torsional stress. This is called as torsional stress. Third and last type which we are seeing today. So take the same example. You have a fixed wall in which you have protruding, let's say, a cylindrical shaft kind of thing, cylindrical shaft, and you are applying torque to this. You are trying to spin it. Okay, you're trying to spin. So it's no longer called force here. Okay, you can't apply force when it is in a circular fashion, right? So you call it as torque. Torque is denoted by mt. Mt is torque. Okay, so you're applying directly the torque, and you want stress out of this. Let's say, so you want to design a shaft, and you have how much torque you're applying. Okay, torque again, units are Newton mm, right? So you need to see how much stress you are encountering in this. So in this case, again, you need to work out a link here. Let's go back to the data handbook. I think the equation somewhere here. We passed by that time. Oh yeah, here, figure 218. Figure 218. Oh, yeah, here. Check out this figure here. Okay, you're applying the torque. Initially, the neutral fiber was here. Now, because of the application of torque, it has shifted to B dash. So point B has shifted to B dash, and you have the deformation in respect to theta. So it's polar here. It's polar in nature, and you have a deformation in terms of the neutral fiber as phi. There are two kinds of deformation. How you can link that is with this equation here, the general equation of torque. Okay, again, ultimately we want the stress values, right? So you can see here the shear stress value tau. So you can get the stress value here as shear stress.
Hello, sir.
Oh yeah, you have any doubt? No. Okay, so let me continue. So I have mt. Let me write that equation. It's mt for torque over J. J is called the polar moment of inertia. Okay, instead of I, it is J. So this is equal to G. G is called as the rigidity modulus. G, rigidity modulus, and theta, that is angle of twist, over L. L is nothing but the length of the body, and this is equal to tau. Tau is the shear stress by rho. That is the density, I guess. Rho is the density of the material, right? So we have all the values here. So this is according to equation 2.86. Okay. Again, for there's a polar moment of inertia. If I were to write for a circular material, is say pi d power 4 over 30. For a circular cross-section, that's how you would write the polar moment of inertia. And suppose you wanted to find the stress value of this. The stress value of this, you would get it extract from tau equal to, just reframe this, mt. I'm sorry, this is not rho, I guess. This is not rho. This is R. tau by r. Sorry for that. I think there is some mistake in the definition in data handbook. So this is not tau, it's r. You make the small change in data handbook. Okay, it's here. Check it out here. So it is this row is nothing but the distance from that this thing. What do you say? Center to that elemental portion. It's just same thing. So mt by j into r. So that's how you extract the shear stress. Okay. So now we have covered the three modes of static load. The next class we'll start off with what is known as what happens if you have combination. So these are all individual cases, right? So these individual cases already you might have solved several problems in previous years, but when you have a combination of these, suppose you have torsion along with tensile and or torsion along with bending. So these cases problems we'll discuss in the next